And it's a great pleasure to introduce the speakers of the second course of this school. So I introduce Professor Anne Friebs Krieger from University of Oldenburg. Hi, Anne.
Hi.
Nice to see you. And Matthias Zack from Kaiserslautern University. We also be responsible for this course. So, the course will be about singularities and computer algebra. And so it's my pleasure to ask you to start, please.
Okay. Hello. Thanks for the introduction. Anne, can you hear me? Are you there?
Yes, I'm here and I can hear you. I just need to see the slides somehow.
Can everybody hear
Great.
Anne? Very good.
Okay. Then we are here to discuss algorithmic methods for singularities, or in other words, how can we use the computer to help us compute stuff that is too tedious to compute by hand. And in the past, those of you who are around for a bit know the answer would have been singular. Use singular. And singular is a great tool and it's behind OSCAR, but OSCAR is a more comprehensive tool in the sense that at times we all had the impression, oh, if I could just work a bit with groups here, I could get further. Or if I could have more tools from polyhedral geometry, I could get further. And in group theory, there is another tool that has been known for a long time, that's GAP. In polyhedral geometry, there's yet another tool, Polymates, that has been around for a long time. So the idea behind OSCAR is not to reprogram everything, but to join together the forces of such specialized tools from different fields so that in one computer algebra system, you can rely on the power of those components and can interchange easily the data between those systems. Moreover, the language of singular was created at the beginning of the 90s and was far from what you would expect from a nowadays language on a computer for programming. So it was time to have a different level of programming also, and that's also done by OSCAR. OSCAR is actually a program written in Julia, modern programming language for computer algebra, for numerics, for everything in mathematics, originating from numerics, and now by OSCAR, translated into the world of symbolic computation. And now we start with our presentation of OSCAR. The first talk will be very low level in mathematics, and it will be a lot about technicalities, how to start, make sure that you don't get stuck in the first lines of what you're doing. And therefore, we have not only prepared slides, we have also prepared worksheets. Worksheets on which you get all our input and some more explanations so that after the talk, you can download a worksheet, look into it, and look, how did we do that? What was the remark on it? What was the problem? And so on. So this will be available to you after the talk, and we'll now directly jump into the first worksheet.
All right.
Matthias?
Yes, I can take over.
Yes, it's your turn to project something to the screen.
Yeah, may I ask the assistants to bring my screen on There? Yes, very nice. So, as Anne said, we have this new system, OSCAR, and the first thing that we need to do with all of you who are interested in this course is we need to put you in the position to really work with this. And I think the most practical thing these days to do is to help you install this on your laptop or any other computer you may wish to use. And I reserved one exercise slot this afternoon to be there to help you with the installation. The installation process, I try to gather the information here. You can do it in the afternoon during the day, already try to do this, but maybe let's not do all this now because it will take a lot of time usually. And instead, let me show you what this looks like when we use it. So I need to start OSCAR. I already have it installed.
Matthias, one thing
Yes.
first, you need to start Julia in order to start OSCAR. That's an important thing that we should tell people.
Okay. That's true. We need to start Julia. So here I try to gather the what Anne has just said. We have the OSCAR system, but unlike Singular, it's not a programming language by itself, but it uses Julia, which is like C or Java or something else, some other programming language. It's even a little more, and it's a very nice framework to put such a project inside. And here what you see on my screen is not Julia, but it's something that's called a Jupyter notebook, which is even more advanced, but it's easier for you for the presentation here. So in the exercise sessions, I will tell you how to start Julia on your machine. It will depend whether you have MacBook or Windows or anything else. And I will also tell you how to start these Jupyter notebooks. And if you are in that situation, you can start up OSCAR with this command, right? And you will find out that it takes quite some time. So we have some time to wait. That's usual. And while we're waiting, let's directly jump into the algebra. So Anne says Singular is in
May I?
OSCAR. Sorry?
May I?
Yes?
So for computing, please stay on the slides. No, not the slides. The Julia, the other one.
My screen.
Yes. First steps in OSCAR. So in order to have any kind of object known to the computer, you have to say what kind of object this is. And the first thing, before even being able to define polynomials, is to have a field. And we have to think about what fields do we want to compute above. So if we take the complex or the real numbers, you know, we represent them on the computer in a numerical way, so they are not exact. But for symbolic computation, we need exact field elements. So whenever we input some element of C into the computer, it will not be exact. So we try to stick to polynomials with coefficients in Q, and this doesn't make too much of a difference. During this course, at some points, I'll point out where you have to be careful, but otherwise, if you start from data over the rationals and you compute, you stay in the rationals, and you can interpret everything in terms of the complex numbers. Of course, we also have finite fields here in the line with GF of 53, or we have integers like the line with ZZ, which is to signify the integers. And I assume that by now we have loaded Oscar, haven't we, Matthias?
We'll see. Let's go back up. Yes. So here was the command to load Oscar. And this is what it looks like when it's successfully loaded. So let's dive in.
So now we can, for example, input QQ to get the rationals.
Yes. It doesn't tell us much, does it?
No, it doesn't. But it says it recognized the command, and that's already important for the user to know the computer knows what I want to tell him. And then we might jump 3 inputs further down, because what we are interested in are polynomial rings or power series rings, but certainly not just fields. So let's go all the way down to the first ring we are defining.
No, let's not be so quick. So as
Okay.
Anne said, we have QQ and we don't use floating point numbers, right? And there's a reason for this, because usually when you work with the computer, you, I hope I'm writing big enough, you're using floating point numbers in numerics. So 1/3 would be 0.3333 and so on. But the point is, this is not really useful in algebraic computations because it's not exact, as Anne says. So what we have in Oscar, first thing is we model very exact number types. That's why we use these types. And also this integer ring here, the second one, it's important because what happens this will be a very big number, 2 to the 1,000. The computer cannot digest it, right? It's memory overflow. So let's try something else. Let's say we take ZZ of 2. It's a number, right? And the computer can take it. And in your mathematical computations, it's very likely that you will encounter numbers that need this feature. So always make sure you're using QQ, you're using ZZ, or what also is important in mathematics is finite fields. Here, the finite field of characteristic 53. It's all there. If you look for it, go to the documentation, you will find it, or ask me, since I'm here. And then, where Anna wanted to jump is polynomial rings. We can do polynomial rings over these predefined fields like QQ and ZZ. So this is a polynomial ring in 3 variables, x, y, z, and that's one way to ask the computer to set it up. Okay, Anne?
Yes, what I wanted to add here was that when you have such a polynomial ring, you want it to have a name so that you can refer to it, but you also want your variables to be accessible in some way. So you have an assignment here. On the right-hand side of the equality sign, you create QQ adjoint X, Y, and Z. And on the left-hand side, you assign the ring to the name R, and you assign the tuple of variables to the tuple X, Y, and Z, and can use X, Y, and Z afterwards for computing. So let's see what was created in the next input.
Again, this tells us only what what it is, right?
Yes, it tells us it recognized what we wanted from it. And if we then use the symbol X and input that, that was a variable. It just says it's X. Yes, it's a symbol. It doesn't tell us much, but we can ask for its type.
And we can use it to write down polynomials.
Yeah.
Just like you expect. So this will probably be important for you sometime later. Everything has a type. If you have ever programmed, then you know that there are integers, there are floating point numbers, and other data types. Everything in OSCAR also has a type. And the type usually is some cryptic thing that you don't want to read and that probably doesn't make sense at first glance. But just be aware it has a type. And we'll get back to that eventually. What is more important from the mathematical point of view is that every element in a ring knows about its parent ring. Right? So if you ask X, what is the parent? Then it will tell you, I belong to the ring R. And we can check that this is really the case by asking this. Right? And we can do so with any other polynomial. Say here. The same thing. Good. Anne?
Please notice that in contrast to singular, in OSCAR, it's a polynomial who knows about its parent, whereas in singular, the ring knew about the polynomials defined in it, which means that you have a different perspective on what you're doing. But you can also access objects in different rings at a certain time without changing some environment, which was changing the ring in singular.
Maybe this is a good occasion to ask, who of you has worked with singular already? Can we see the hands? Okay, Anna, I don't know if you can see this. I would say this is about 15 to 20%. No, maybe even more, 20 to 30. Okay, so everybody else has not worked with singular yet. And yeah, let's see.
And just sticks to the explanations on OSCAR, but still I will explain the pitfalls when migrating from singular to OSCAR to those 15 or 20% who are there.
Okay.
So we have looked at the parents, and now we define a different polynomial ring, but this time we don't want to bother to think out 5 names of variables. We just want a list of 5 variables that we can name explicitly, like W of 1 to W of 5. And to do that, we can do it with a range of indices for the symbol W instead of stating just the names of the variables. You see the syntax in the highlighted line here on the slide. If we do that, we create again a ring, and you see it did precisely what we wanted. We obtained 5 different variables named W1 to W5, and we can just type in W of 3, for example, and we obtain the same as W before.
So that is the ring that we set up, and now we can ask for each one of the variables like this, right? We can again ask, what does this variable belong to? Which ring? And here we see W2 does not belong to R. It tells us, no, I have nothing to do with the ring R before. But the ring that we set up here, it's called S. Let's check whether W2 belongs to S. We're lucky. No surprises here. Good.
But of course, everything we did up to that point is rather boring, because what we actually want to calculate with are ideals, matrices, real mathematical objects. So let's directly jump to defining more mathematical objects.
Questions up to this point? No? Good. Then let's go ahead. Yes, yes? With the curly bracket, right? Maybe
What was the
somebody
question,
thought about it.
Matthias?
Sorry?
What was the question?
Yes. The question was, let me repeat the question this time. The question was whether the output that we get is made so that it is ready to be used in LaTeX. And I'm afraid that this is nothing that you can rely on at this point. The output is undergoing constant changes, unfortunately. I should say we're actively developing Oscar. Oscar is still a child, I would say, a grown-up child, but we're developing it all together with different universities in a big research project. And this is all on GitHub, and you can follow all the discussions there and even contribute if you like, if you're interested. Talk to us. And on the other side, that will mean that you will also see some changes from time to time. So maybe somebody thought this would be nice for LaTeX, but I'm afraid nothing to rely on at this point. Good.
But of course, if somebody would like to contribute some kind of tool to transfer the output of certain important routines to LaTeX, this would again be welcome in Oscar. You can contribute, as Matthias said. Could we get back to the worksheet, please?
Good. Matrices, ideals, and modules. I guess the worksheet will be on screen very quickly again.
Yes.
There we go. So we take our ring R from before, and we want to set up a matrix over it. This is the syntax. We just describe the two rows of the matrix. And note that as a separation between the entries of the row, we use blank spaces, right? And a semicolon for starting a new row. And there we go. This is our matrix. And this was not. I think if we used a comma, then we would get an error. So this is also something that you will encounter quite frequently. These slides have been prepared, but if you're working with it, 90% of the time you need to find out what you did wrong. So this is one of the things you can do wrong. And also here I created some examples where you should be careful. It's a pity I already spoiled the answer. So the first one here, it's the second variable of the ring R squared. That's y squared. The next example is a matrix. And this is something that you have no way of knowing it before. But it's a trick. You write a semicolon, but you don't start a new row. And then it does a matrix. So you need these tricks at some point, right? And then it has the matrix over the ring R with one entry, which is 2, and squares it. It must be the matrix, the 1 by 1 matrix 4. And then there's another thing. Remember the matrix M from above? You can access the matrix's entries and ask which is the 1, 2 entry of M. So it says it's Y. Let's go back up and see. Ah, that figures, right? There. So that's how you set up matrices. You can ask for the minors of a matrix. And it will give you a list of minors. The bad thing is you don't know in which order they appear. So if you want a specific minor, you have to ask for a submatrix first. You can do it like this. What you see here is a range. You already saw a range when we set up the second polynomial ring, right? This is the range from 1 to end. And it's the end of the matrix, right? So end is a joker. And then the other is 1 to 2. So it's the 1 to the end to 1 to 2 submatrix of M. And if you compare this to the above, let's see. That's okay. It's the right matrix, right? And you can also do other submatrices. Now here, this is not a range. This is a vector of indices. First column and third column. Delete the one in the middle. You can do that. There we go. Okay? And then if we want a specific minor, we can also take the determinant of these submatrices. Good. That's about matrices. Anne, anything you want to add?
Not for the time being, because we have to speed up a bit to get to something which is a bit interesting in this first part of the lecture.
That's true.
So maybe we speed up a little bit and show how to define ideals.
Good.
Because
Ideals.
as soon as we have an ideal, we can put this to work in a very simple case, namely computing a singular locus. But for the time being, we first need to define ideals. And here, for the ideal, we have to tell the ideal what ring it belongs to. And then we can specify the list of generators. Again, as before with the polynomial, an ideal needs to know what ring it lives in, and of course this data has to be given. Please be aware that an ideal is truly an ideal in OSCA. It's not a list of generators. So you would need to write generators of I, gens of I, to get the list of generators. Otherwise, if you say I, you just specify it's the ideal without specific generating set. Now we can test whether some polynomial is in I, like here.
Is x plus 1 in I? Still, you can take bets. Oh, it's over. No, it's not.
It's not, and that's actually in the background a Gröbner basis computation, a Gröbner basis for I, and then a reduction, and we'll come to that later on. But for the time being, let's just take another test whether a polynomial is in I, this time for a polynomial for which we see by eyeballing it that it is in I. The next one.
This might actually be the first instance of some place where you need a computer, right? It's if you ever try to check ideal membership by hand for a non-trivial case, then you probably sooner or later bite your books or something, right? So this is something that OSCA is good at and that it can do for you. So let's give it another challenge. Here I was cheating a little bit. If you look at this more closely, then you see that I took a linear combination of two generators, right? So this should be an I. We're lucky, right? So, and one more thing that you can ask is, if you have an element in the ideal, please give me the coefficients of the linear combination that I need, and it will give you some coefficients.
With
Good.
respect to the original generators of I that are still stored away somewhere and that you can recover by saying gens of I in the order in which you get it back. And now we go to the slides, please.
Good. Back to the slides of Anne, because we need to prepare the theory to come to geometry and varieties and singular loci. Please, to the
Could someone
regie.
please put the slides in the picture?
Yes,
Thank you.
Anna, I was
So-
informed that the changes take some seconds
Okay.
usually, so we should be a little patient, and
It's okay.
now it's there.
So, of course, you all know the Jacobian criterion, in particular if you're dealing with an equidimensional situation, that is, your variety or germ consists of components which all have the same dimension. In that case, it is easy to check that X is singular or regular at a point P by just checking the rank of the Jacobian matrix of a given set of generators at the respective point. And if it is smaller than the expected value, n minus the dimension of x, then of course your x is singular at P. That's known to all of you. And the singular locus is of course a vanishing locus of those minors. But we want to do it by a computer. So let's check, can we do all this? Can we take the derivatives or the Jacobian matrix? Yes, there is a command for it. We have already seen we can do minors. And we'll see in the second talk how dimension is computed. For the time being, just believe me that we can compute it.
So should we switch back to
And
the
let
worksheet?
me just name two examples. The first example is a really stupid one. Takes the two coordinate axes in the plane and take a line not going through the origin. In this case, the line x plus y minus 1. Takes the union of those three components. Then you all know they intersect transversally. We have three singular points where they intersect. So we know what will come out of the computation of the singular locus. And the second example is a more complicated ideal. For that one, we can also calculate the singular locus.
Good. Anne,
So-
maybe you don't see this, but I'm drawing a picture of
I'm
x.
seeing it because the technician already put you in the picture. That's
Okay.
precisely the picture we had. And now it's time for the Oscar notebook again.
All right, let's go back to the Oscar notebook. So let's put this in the computer, what you just saw on the slides. You have the equation for x and the ideal associated to this. And now let's try to find out whatever we need to find out. First, the dimension. Oscar has data structures to handle varieties, but let's stick to the algebra part for now, since this is the more familiar thing. We ask for the dimension of the ideal. It's 1. And this is also what the picture suggests. We have a curve. Then let's find out about the Jacobian matrix of the generators. Something else that you can do by hand, but the computer will beat you in being quick. In particular, in more complicated examples. And then we need to assemble this ideal for the Jacobian criterion. So we take one by one minors, which seems a little superfluous, but it's the most convenient way to take entries out of a matrix to generate an ideal. So we take the minors of the partial derivatives of G, and we add the original ideal I. And one thing that I should maybe mention here is with the output of output number 38. Sorry, I need the slides back. The Jacobian matrix, it's not a row matrix here. Most of you might be used to writing this as a row matrix, but it's a column matrix. And Oscar, for some reasons, people have decided to go with the other convention in Oscar. Every matrix is flipped compared to most of the literature. So don't be surprised by this. Good, we have the ideal for the Jacobian criterion, and it's a very nasty set of generators here. And as you may all know, if we're only interested in the geometric locus where things are happening, we can take the radical, and taking the radical is also usually, there's hope that the expressions are more simple that you get out. And more human.
On the other hand, the radical is a procedure, a function which is rather heavy. So if you can avoid it because you already see by looking at it what comes out of it, then avoid it. But otherwise, a radical is something you can compute, but maybe you need to wait for a moment in more complicated examples. So just be aware that radical is not a procedure you call and then with a flick of a second you always get an answer. It can take a while because it's computationally heavy. Here with the output we see that Matthias, you moved out of the screen.
It has jumped.
Here with the output we see already that we certainly have more than one component, as we would expect from the picture. And to get the components, you can compute a primary decomposition.
Of course, we all know what the solution is from the picture, right? And if you sit down and do all the computations, you may eventually find these equations here. But we can also be very lazy and ask the computer for a primary decomposition. And then we get a list of tuples with radical and component, honest component of all the components of this ideal. And here it's already easier to read off which component is which one in the picture, right? We have the x equals 0, y equals 0 component as the first one, y equal 1, x equals 0 here as the second, and so on. So you still need to do some interpretation work from the computer output, but you can bring it together with the picture. And then if you have a complicated procedure like this one, this is not really complicated, but nevertheless, you don't want to type everything at once, every time you use it. You can wrap this up in a function. This is a Julia function. And you can say, I put in an ideal I, and then I do all the steps that I had before. Compute the dimension, compute the base ring. Ask the ideal what ring it belongs to. Take a list of generators, Jacobian matrix. Find out about the codimension, right? You need the dimension of the ring, you need the dimension of the ideal. And these numbers go in here for the size of the minors. and then return the radical. And if we do that for our ideal from before, it gives us a convenient shortcut.
Now we would need to switch back to the slides, please.
Yes, Anne, but it's 1:15, and I think we're
We
forced.
started 5 minutes late, and I want to jump to the next thing that I really want to put into this part of the lecture. And that is, whatever we showed up to now was in the affine situation. We were looking at polynomial rings over Q or over some other field. We were not looking at power series rings. We were not looking at space germs. And as we said at the beginning, that for exact computations, we need exact fields, which is to say, for example, Q or finite fields. Here for the rings, we have the same restrictions. We need rings with exact computations. So we can only go to the, great. Could you switch back just for a moment to the localization at, no, not there, to the previous slide. There, yes. We can do computations in the localization of a polynomial ring at the origin. That's where we can compute, and in the same way at other points, but we cannot compute in the power series ring in an exact way. There we would again do approximations by cutting the number of terms of the power series to a finite number. So in the end, we are reasoning in the power series ring over the complex numbers, but we will compute in the localization of the polynomial ring over Q at a point with Q coordinates. That was the thing that I still wanted to say at the end of this lecture, because as I see our time is up.
Okay.
And after 5 minutes break, we continue. Is that right?
Yes, yes. After 5 minutes, we continue.
We come again after you ask your question.
I hope Anne is also with us again. Very good. So one thing I wanted to say is the worksheets for these lectures, they will be available online. And in particular, you will find the installation instructions that you saw in the very beginning there. And I will ask Raimundo to put the link on the school's website, where you also find the other course materials, right? So after this lecture, we will update the links there. And I was asked to give you the opportunity for questions again, since before the break we skipped the questions. Are there questions? Yes, please.
Good morning, Professor. This is a little more on the technical side related to how Julia works. So there are these two types of languages in, let's say, they call strong type and weak type. Strong type is like singular, where you are asked to give a type for everything you input. For example, if you write f equals, like let's say you want to input the polynomial xy squared. Yes, I'm waiting for, okay. Yeah, so for example, if you don't write poly at the start, then the singular will throw an error because it doesn't recognize what type is f.
Right.
Then you have weak types like Python, if you're used to it, or Julia itself, where the type is inferred from the information.
Yes.
In fact, Julia, I don't know if this is a common feature of weak languages, but Julia allows both. You may give a type or you may not give a type. But in fact, the developers discourage you from giving types unless necessary, because Julia is designed in such a way that it can infer the type and do optimizations based on those inferences. So my question is whether Oscar works on the same fundamental basis of try and use weak types unless necessary because it will run faster, so to speak.
Can you say I didn't understand the last part. Whether Oscar does what?
Whether Oscar also works in the same principle of try and use weak types as much as possible so that the compiler does optimizations based on
Yes.
inputs.
Yes, it does.
Yes, it is in the pure tradition of Julia. Julia was chosen as the language to write Oscar in just because this is one of the features that the authors wanted to have.
Okay, that's it. Thank you very much.
Good. So in Oscar, as in everything in Julia, the type can be inferred from the variable, but you have a lot of fine-tuning possibilities by being careful about types. But that's more a Julia thing, not so much of an Oscar thing at the moment. You will encounter that when you do advanced stuff. Yes. For the moment, just see that things are a little bit more simple than in Singular for the start.
And Matthias, I would
Yes.
suggest that we now first do that little overlap on the worksheet 1 on localization, because that is vital. And then we switch to my slides, and while I explain the beginning of talk 2, then you can change the worksheet.
Okay, so we continue with the localizations. Is that right?
Yeah.
Good. Please, my screen on the screen. So,
Yes.
where did we leave off before the break? Anna was saying
We
did-
left off. Oh, sorry, that was not a question, that was a rhetorical question. Sorry.
Yes. So, as Anna said, up to now we did all the computations in polynomial rings. And that's maybe the natural setup, because in polynomial rings we have Grödner basis and all the needs, for the machinery to do stuff like ideal membership tests and so on. But in Oscar we can also do local rings. So let's see how we do a local ring. What you do in singularity theory is usually you look at a variety at the point, the germ of a variety at the point. And on the algebraic side, as you may know, the algebraic translation of this is to localize a polynomial ring at a point. And we can do this as you see here. The ring, let's say the ring is again in 3 variables. That's the first line. Then in the second line, we do something that might seem weird. First, we set up a multiplicative set, the complement of a maximal ideal in this case. The complement of the maximal ideal corresponding to the point at the origin. And that's one of the differences to singular. We have a data type for these sets. And then we can do the localization of the ring R at this set. Let's see what we get out. We get out 2 things. First thing is the ring L, and the second thing is the natural map from the ring R to L, right? To recognize a ring element as a fraction. Good. And then once we have done this, we can do computations. So what we see here is an element of the ring R. And then here we cast y minus 1 to a fraction. So maybe let's see what L of y minus 1 is. That's a fraction with a trivial denominator. And we can also take the inverse of this, as we do in the above line. And it's an admissible element of this localized ring, because y minus 1 is a unit. Right? And then we can add it with elements of R, and Oscar automatically realizes that if you put something of R and the localization together, then probably you want to do stuff in the bigger ring in the localization. And that's what you get out. So the output A from the previous computation is an element of the localization. And then also mathematical comparison works as expected. So the double equal is mathematical comparison. If you want to do comparison of the things, of the objects in computer in the memory, you have another operator, which is the triple equal. And that will tell you, no, they're different ones. So you will eventually find out about this when you start working with it. Good. Anna, how do you want to proceed?
Just go all the way to radical of singular locus.
Skipping or doing it quickly?
No, just do it, because it is important that really in the localization we don't see the other singular points.
Okay. So here, let's do geometry again. We set up a variety, and it is now a variety that sits in 3-dimensional space. It comes from, it has one hyperplane, which is defined by this equation z minus 1. And here it has a cylinder over a smooth conic. Why a cylinder, or what do I mean by cylinder? I mean the variable z does not appear in this equation. And then we take the union by taking product of generators. So let us find out about the singular locus. Remember that before, on the previous slide, before the break, we have written a function that does everything for us. And here we go. This is the singular locus. So let's investigate a little further. Nothing more useful about this. Okay.
So now we can map it to the local ring, and that's just done by telling the computer that we want to consider it as an element in the local ring L.
Okay. Let's do that.
And now, of course, we could check that it is in that new ring.
Okay. Yes, it's an
Do
ideal.
you do anything else with that ideal? Down there?
Sorry?
No. Do you have anything else? No. Then that is about what we should do on that slide to save a bit of time, and then really go to the slides.
Look, this is the one crucial thing.
Yeah, okay.
The one is in the localized ideal, so it's trivial in the local ring. Why is that the case? Well, we had a picture in 3 dimensions. We had z minus 1 as a component, right? So this hyperplane and a smooth conic, I think, must have been like this hat. And if you localize at the origin, then you find that the singular locus, which is this intersection here, doesn't touch the origin. Okay, if it touches the origin, it's only due to the perspective here, right? So this is how you can verify that Oscar, when you pass to the local ring, it says no singular set, because the singular set is far away. Good. Anne?
Yeah, then let's move to the slides.
We need Anne's presentation back on the screen. Anne's presentation, can we bring it back to the screen, please? Assistance? Okay.
Yep.
Very good.
There it is. And in this talk, which now starts somewhere in the middle of the second talk, we wanted to look at invariance from the computational perspective and show you what to think about if you want to calculate some, say, numerical invariant, and what you can do to turn your mathematical ideas into an algorithm. So let's start with something you know about dimension. You all know if I have a hypersurface in 3 space, that's surface. If I have a plane curve, that's a curve, that's dimension 1. You have a notion of dimension, but how could we phrase this notion of dimension exactly? How did you learn about this notion of dimension originally in the lecture? There are many ways in which you could have seen that. The most common in algebra lectures will be cool dimension, so the maximal length of chains of prime ideals in your ring. And this is also the one which is most inaccessible to computation. but it is geometrically very intuitive because it refers to chains of subvarieties, each being a subvariety in the next one. Of course, the other way around in the inclusions compared to the prime ideals. You could also talk about the number of generators of an M primary ideal. That is, what is the minimal number of hyperplanes by which to intersect at the point so that you get down to a point. And you could, of course, go back to field theory and say we look at the degree of transcendence of the total field of fractions of our ring. That's also a notion that is quite common for dimension and that is used widely. The next one is Noether normalization. We know that in the quotient of the polynomial ring by an ideal, we'll find some polynomial ring in some elements y1 to yd of the original ring, and that this is finite and injective map. And here D would be the number of those yi that you have in that ring. Geometrically, it corresponds to projecting dominantly to some affine space in D variables. And the last one is the one that looks the ugliest. It's the degree of the Hilbert-Samuel polynomial. But on the other hand, it is the one which is most accessible to computations. So when you think about what's going on, you would think in the sense of length of chains of prime ideals, of intersections with hyperplanes, or in the terms of projections. That's the geometric thinking you have. And you would always say, oh, that is the degree of the Hilbert-Samuel polynomial, that's just a coincidence. But for computing it, this is the right notion to attack it, because that one is truly computable. And the last two, Noether normalization and the Hilbert-Samuel polynomial, are accessible to computation, while the other three are not. So let us look at the Hilbert-Samuel polynomial. We look at a local ring, and the Hilbert-Samuel function just looks at the dimensions of A modulo the powers of the maximal ideal. And in this sense, of course, you know, the values are strictly increasing or at most getting stationary at some point. But it is just a function. It's a function assigning to a natural number another natural number. So that's something you can compute, but not for all k in that way. Luckily, there is a result which says that as soon as k is large enough, there will be a polynomial with coefficients in the rationals such that the Hilbert-Samuel function evaluated at k will be precisely the value of evaluating the Hilbert-Samuel polynomial p at k. So we know that after a certain point we have a polynomial description. And for the Hilbert-Samuel polynomial, if we write it down as a polynomial, we can read off the dimension of our ring A from its degree, and we can read off the multiplicity from the leading coefficient adjusted by the factorial of the degree. So dimension and multiplicity can be computed as soon as we can compute the Hilbert-Samuel polynomial. So let us look at a very simple example, the 3-coordinate axis in 3 space. Here I have written down the ideal, and now we can look at the new monomials that come in each degree. So if we take modulo m, then we just have the 1. and of course it's 1. If we take modulo m squared, then of course we have all degree 1 monomials new in here, and the total number from top to that line is 4. When we take modulo m cubed, for the first time something is happening because 3 generators all happen to be in m squared, and they are killed, whereas the pure powers x squared, y squared, and z squared survive, so we get to 7 here. And of course, then from then on, nothing new happens because here we don't get any further contributions that we have not yet seen in higher degrees. So we know from here on, it will always go up by 3 with each incrementing of k.
Anne,
Yeah?
I don't really understand what the content of the table is. Can you repeat that? Because I I think maybe
Okay,
also
I'll
not.
go one slide back, and our Hilbert-Samuel function is a z-dimension of a modulo m to the k.
Okay. So
That is what we want to compute from a certain k on, and that should be then in the end polynomial. So keep in mind we want those C vector space dimensions of a modulo m to the k. Now for k equals
wait,
1.
just one question. The A is the localized polynomial ring, or is the quotient by I?
It's the quotient by I.
Okay, let's so A.
It's the quotient by I.
We have this localization of the polynomial ring at the origin, written like that, and then here
Modulo I, exactly.
modulo I, and your example is the 3 coordinate axis, where
Yeah.
I is equal to x x times y.
To the 3 non-pure powers in m squared. Yes.
And y z.
Z.
Right?
Yeah.
And I started to print a monomial diagram here, maybe
that
in 2
doesn't-
dimensions.
It doesn't work for the 3-dimensional case. That's why I made a table here.
Yes.
But if you look at the table, here you see you have just 1 degree 0 monomial. That's the 1 in A mod m. In A mod m squared, of course, you have additionally the monomials x, y, and z. So in total, you see 4 monomials. Then if you go to A mod m cubed, of course, everything that you had mod m squared is still there. But now in degree 2, you have 6 potential monomials, the 3 pure powers and the 3 non-pure powers. The 3 non-pure powers are in I, so they don't appear. And what's left are the 3 pure powers. Now we are in A mod. No, Matthias, we are
Yes?
in A mod m cubed. We are in A mod m cubed.
Okay. So A mod m had just one thing.
Yep.
A mod m squared had
Had
2
x,
things.
y, z, and the one from above.
Yeah.
And A mod m cubed has the 4 from above and has the pure powers.
Okay. X squared, y squared,
Y squared, z
and
squared.
z squared. So
Yeah.
the question is, what about x times y? Right?
That's in
This is
I,
also
and we modded out I. It's in I. We modded out I because A is the localized ring modulo I.
right, and that's why it's gone.
Yes, exactly. And then if you go to A mod m cubed, then you know all mixed monomials will be deleted because they are in I. Only again, the pure powers survive. And that will be the case in all other degrees. So in total, you see from here on, we will always get 3 new monomials in each incrementation of k. Are you now following? And is the audience now following?
Yes, I think it's fine. Questions? All right, let's go.
So we know that it will be 3t plus or minus some adjustment that we then compute from the total numbers we have back here. And from that polynomial that we could read off as soon as we were beyond degree 2, from that polynomial we can read off that the degree is 1 and the multiplicity is the leading coefficient times the factorial of the degree. So it's 3 times 1 factorial, so it's 3 as expected. And now you could say, well, that was a bit of combinatorics, that was easy, we could do that. Can we also do that in more general examples? And then the answer should be no, not really, because the lucky situation was that we have a monomial ideal. In the non-monomial case, we need to assign a monomial ideal corresponding to our original ideal to the whole thing in order to compute it. So that's the first time where we really talk about standard basis computations, where we talk about finding a monomial ideal that's sufficiently close to our original ideal. So in our situation, we need to be using an exact computable field. I talked about that in the first lecture. We need to put a total ordering on the set of monomials in our variables, and this total ordering has to satisfy further conditions, so I say a suitable total ordering. The leading term of f should be the largest monomial with respect to this suitable total ordering on the monomials among those monomials appearing in f. And the leading ideal of I is, oh, that's the wrong kind of brackets here. I need to correct that before uploading the slides for you to download them. That should be angle brackets. It's the ideal generated by the leading terms of f, where f is an element of I. So the ideal generated by all leading monomials of all elements of I. Exactly, that's what I need, and there I have the wrong kind of brackets. And similarly, for a finite set of elements, say G1 to Gs, we can define L of G as the leading ideal of that set, that is the ideal generated by the leading terms of that set. And now, such a set of generators is a standard basis of I if and only if the leading ideals of the set G and of I coincide, and G, of course, is a set of generators of I. Now, the thing that we can use to compute dimension and multiplicity is that if we have the ring modulo I, we have the same dimension as the ring modulo L of I. And by computing a standard basis, we can compute L of I from a finite set of monomial generators that we have in our hands as the leading monomials of the elements of G. So we can compute the dimension by computing the dimension of the ring modulo the leading ideal, and same with the multiplicity. And the leading ideal is a monomial ideal, so the computation is purely combinatorial, and we also know that we have K large enough so that we can start looking for the polynomial as soon as we have gone beyond the last leading monomial of G in our K. So standard bases are what make dimension and multiplicity in this sense computable for general ideals, because they allow us to take a set of generators so that we can assign the leading ideal and the leading terms of the GI are the generators of the leading ideal. So we have finite data in our hand from which we can compute dimension and multiplicity by computing a Hilbert-Samuel polynomial from this monomial ideal. Now let us look at an example for standard bases. Here I take the ideal generated by x squared and y squared and by x times y. It's a set point in the plane. And I take as an ordering a good local ordering by the name of negative degree reverse lexicographical ordering. The name isn't really relevant here. Relevant is that the word degree appears in the name, and negative is for local. Then we look at the leading terms of our two generators, x squared and xy. Now one could think, okay, just take the ideal generated by x squared and xy. But in that ideal, we wouldn't have a pure power in y. But y times the first one minus x times the second one gives us y cubed. And therefore, y cubed is an element of I, and therefore also, because it's monomial, an element of L of I. So that one was actually missing. And if we go on computing, we'll soon find out that this is already our standard basis. We have the generators x squared plus y squared and xy from the beginning. And we have the additional generator y cubed that we needed to add because all pure powers of y are in I, starting from y cubed on, and therefore y cubed itself needs to be in the set of generators, and its leading ideal, which is again y cubed, needs to be in L of I. Now let's look at a different example. Here I take an S5 simple space curve singularity from Justice list, the simplest one which is there, and I take again negative degree reverse lexicographical ordering. I get the leading ideals x, y, and z squared, which happens to be a standard basis here. And for the ideal generated by those leading ideals, I can do basically the same table as before because it's monomial, and we can compute dimension and multiplicity from it. So that is what I wanted to tell about computing dimension. And now the question is, how much time do we have left?
5 minutes we have, so we can quickly have a look at the next
So
workshop.
let's have a look at the Jupyter Notebook and restart with Milner and Turner number tomorrow morning.
Good. Can we get my laptop to?
We have it.
Yes, very nice. Thank you. So first thing is I started Oscar again. And let's see about dimensions. So I'm afraid I don't have the same examples as Anne, but I don't want to start typing now because we're very short with time. So let's just stick to the examples that we have here. What do I have? I have 4 variables, right? And I'm doing a weird construction. I first set up a matrix M. Let's look at the matrix M quickly. Here, there's M. And I take the 2 minors and the ideal I generated by these 2 minors.
So that's what you'll see in a later part of the school when it's about determinantal singularities, that this is a determinantal singularity.
Okay. And we need the monomial ordering that Anne has been talking about. So one question, who has seen monomial orderings before? Can I see some hands? So Anne, also for you, this is probably not even half of the people, right?
I know. And I just introduced them as a black box, saying we need a suitable total ordering on the set of monomials, and Oscar provides suitable orderings for that.
Good. So let's see what commands we need for that black box here in Oscar. We have the ideal I from above, and we can compute a standard basis. At this point, the command is std basis, similar to singular. And what we get out, well, it takes some time. And we get some generators out. So leading ideal is also occurred, can be asked for with the command leading ideal, but here a little bit special the way you call it. The sheets will be online, you can see them. And the Hilbert polynomial. So the Hilbert polynomial is a little bit complicated. You first need to put a grading on the ring R to make it a graded ring, as you know from projective geometry. Then we need to translate the leading ideal to the graded ring. I'm sorry, this is unfortunately a necessary intermediate step. Later you can wrap it in a function. Then we need to do quotient rings. This is something we haven't seen before. We have seen polynomial rings. We have seen localizations of polynomial rings. Now we do something like this, but without the localization for the moment. We do this with the command quo. And for what you have, what comes out there, we can do Hilbert polynomial, just like Anne has presented this on the slides.
Yes, except that this is the classical Hilbert polynomial that you're presenting, and I presented the Hilbert-Samuel polynomial in the local case. So the sum over the graded pieces up to a certain point. But both are available.
Good. Maybe we can quickly clarify tomorrow the connection between this Hilbert polynomial and the Hilbert-Samuel function. But I think for today we're out of time, right?
Yep.
And we should come to an end. So that's it. Thank you very much. Microphone. There's one coming.
So my question is the following. In the example by Anne of the computation of the dimension using the Hilbert-Samuel function and the polynomial,
Yes.
so you need that K is big enough.
Yes.
Okay, so in practice, how do you know that your K is big enough?
You know that from the monomials in the leading ideal.
Sorry?
So you're computing a standard basis.
Yes.
The standard basis contains, of course, a certain finite number of elements. Each of these elements has a leading monomial. And as soon as you are beyond the highest degree of a leading monomial occurring among the leading monomials of your standard basis, you know that you don't have any new contributions, and from that moment on, you can start determining your polynomial.
Okay, thank you.
So it's actually because it's finite data that you get from the standard basis
Because
computation.
it's a monomial idea, no?
It's
It's
monomial
because-
data. It's a finite number of monomials, and as soon as you have passed the last one, you're fine.
Thank you.
Do you have a routine for calculating the multiplicity of an M primary ideal in a local ring of a variety?
You mean of an explicit one? So you have
Well,
a Samuel multiplicity.
Yeah, I
You
mean,
mean
it looked
you
from your
have an
example where
explicitly
you're
given-
using, it looked like you could compute the Hilbert-Samuel function for an ideal and then just read the multiplicity off from that.
Yes. Yes, basically that's what you can do.
Yeah.
If it's sufficiently explicit in the way it is given.
I'm sorry, could you say that again? I really didn't hear the last, it was a little bit garbled in my ear.
If it is sufficiently explicit in the way it is given, you cannot just say take an M primary ideal. You need to input an explicit M primary ideal.
Right, so I have to write down a set of generators for you.
Exactly.
Yes, right. Well, of course I would do that. Thank you.
Thank you, Anne and Matthias, for the nice and synchronized talk. Very nice. I have the following question. So
Your microphone is muted.
work with models.
Sorry, your question didn't arrive properly. You muted in the middle of the question.
No. Yep. Please, is it possible, do you have a routine to work with finitely generated models? Because this appears in the, for instance, in the course about ICES, right? To compute the K-tangent space, for instance.
So yes, there are routines for finitely generated modules, but they are not as far developed as the ones for ideals. You'll see something on finitely generated modules tomorrow and also next week. And yes, there is stuff, but not as much stuff as for ideals currently.
Thank you.
But it's coming.
Yeah.
Yeah.
You're muted again.
Is
I got
okay?
it.
You got it? Okay. Just please wait for my signal upstairs.
All right.
Hello. So let's start with the following course. So it's my pleasure to introduce the next speaker. Is Laurencio Maxim from the University of Wisconsin, Madison. And he's going to speak about the topology of complex projective hypersurfaces.
Thank you for the introduction. Can you hear me well? All good? So I should say that I have no, no interest, let me put it this way, in recalling everything I said in the recorded lecture. So I should say that there is a set of recorded lectures in a folder which is posted on the conference side. There are 4 recorded video lectures and 4 PDF files with the slides written during the lectures. There is also an overview file containing all lectures, and I just added this presentation with some exercises, and this is more like a summary of what's, let's say, what's contained in 3 of the 4 lectures. Most likely I will not go over the last part because it may complicate the matters a bit. And I'm not sure this is the right thing to do, but in any case, if you want to see more about the topology of hypersurfaces, there is a whole world out there about the actual hypersurface and then about the complement of such a hypersurface. So the topology of these 2 spaces are of course related, but they have also separate lives. All right, so this is more like an overview, as I said, and I transformed some of the examples that I had on the slides initially. Let's skip the... Huh? Someone scary in there wants to see the lectures. All right, so some of the examples I had on the slides initially are now transformed into exercises, and we will go over them time permitting. I should say that I would rather finish the slides, however long it takes, and then go over the exercises. So that may change the structure a little bit. All right, so let me start with the setup. I have a everything will be in the complex world. We work in the complex projective space. You can work also in the affine space if you like, or you can work locally. So you'll see some of those aspects also in Dirk's lectures, or you saw them already. And for the affine part, Cesar talked about polynomial maps a little bit. But I will focus here on the homogeneous case in the projective situation. Okay, so this is becoming annoying. There's no one there. So what is a projective hypersurface? I work with a homogeneous polynomial in n plus 2 variables in my case, and I take the 0 locus regarded as a set in the projective space. This is possible because of the homogeneity of the polynomial. So this is for us a projective hypersurface.
Excuse me.
Go ahead.
I think microphone is not working.
Okay. Yeah. No? There was someone there, perhaps. Is it? No?
Okay?
How about I put it in my pocket? Maybe he likes it better that way. All right. Okay, so what is the singular locus? We already saw this also. Take the Jacobian, well, take the partial derivatives and take those points on the hypersurface, or the partial derivatives of the defining polynomial vanish. And as I said, we're interested in the topology of the hypersurface, of the zero locus of the polynomial. And by this, I mean computation of various topological invariants like the fundamental group, Betti numbers, Euler characteristic, and more. I mean, you can do hash theory, but this is, of course, not something I plan to do here. So this is typically referred to as the shape of the hypersurface. And as I already mentioned in the introduction, the shape is tightly connected to the topology of the complement of the hypersurface, or what people usually refer to as the view from the outside of the hypersurface. Now, this view from the outside is inspired by the theory of knots and links in spheres. I didn't do that. Okay. So if you take, for example, a knot, what is a knot? It's a circle in the trisphere, but the circle is a circle. Its topology is very simple. But it turns out that if you actually look at the complement of the circle in the trisphere, not all knots look alike, right? Some of them are knotted. So this is the perspective we take when studying complements of hypersurfaces, and the study of such complements brings a lot of information about the hypersurface itself. Okay. So let me start with a result just mentioning something that you'll see in Dirk's lectures later on. This is a result of Dimka Papadima, which goes into the direction I want. If I take a generic hyperplane, so generic here means transversal in any sense you like to the hypersurface. So the hypersurface is going to be a union of manifolds, so it's going to be stratified. And genericity here means transversal to each piece of the stratification. Then the affine hypersurface obtained by taking the hyperplane slice out of the original projective hypersurface is a bouquet of spheres of dimension equal to the dimension of the hypersurface. Real dimension of the sphere equal to the complex dimension of the hypersurface, just like in the case of the Milnor fiber. And how many spheres appear there is the number, well, is called the polar degree of the defining polynomial. So this is the topological degree of the Gauss map that one can associate to the defining polynomial. As I said, you'll see that, I'm sure, in Dirk's talks. But why did I want to bring this up here? Because one of the Fields medalists for this year had a lot to do with the study of polar degrees, and it generated a lot of work that was done by Dirk Siersma, Mihai Tibor, Stimbring, and some other people, I guess. And it kind of fits nicely with our situation, right? So I want to look at the projective hypersurface itself. And you see, if I take out a generic hyperplane from it, what's left is just a bouquet of spheres. So the topology is very simple. However, and this is the warning I want to write down here, it is difficult in general to glue the affine piece and this generic slice to obtain useful information about the hypersurface itself. Even though the pieces are easy, well, easy. I mean, of course, the slice, the difficulty here is in the slice. Okay? So this is the last thing I'm going to say about the polar degree, and now things are going to become very elementary. Okay, so computational tools. So how do we actually study projective hypersurfaces? This is a classical topic. It appeared in books already. So I'm going to take a polynomial, homogeneous polynomial of degree d, defining our hypersurface, and look at what's called the affine cone on the hypersurface. So this is the hypersurface in the affine space of dimension 1 higher, defined by the zero set of the same polynomial. But now I'm not looking at this as a projective situation. Then there is a global version of the Milnor fibration that you saw in a bunch of talks already. So in the homogeneous case, the complement of this affine cone in the affine space, fibers over C star, the defining map of the fibration is the map F itself. And here the fiber can be just taken to be the affine hypersurface given by any level set of the function. So just take F is equal to 1. And whenever you have a fibration over C star over a circle, there is an associated monodromy homeomorphism to it. And this is what I'm going to call H. So our situation of a projective hypersurface has naturally attached to it a Milnor fibration on the complement of the affine cone on the projective hypersurface. And I want to actually say a little bit about how to say something meaningful about the hypersurface just by looking at the Milnor fiber. All right. So if the hypersurface has singularities of, let's say, dimension S, then results of Milnor and Kato Matsumoto say that the Milnor fiber has some degree of connectivity depending on the dimension of the singular locus. And it is in fact n minus s minus 1 connected. So this means the homotopy groups of F are trivial up to n minus s minus 1. And if the hypersurface is non-singular, we set S to be minus 1. So in that case, you're only looking at an isolated singularity of the affine cone at the origin, and the Milnor fiber is just like the classical Milnor situation, just an isolated singularity. The Milnor fiber is, in this case, a bouquet of spheres. Okay? Now, if I take the tautological map from F to the complement of the projective hypersurface, this is a D-fold cover, D being the degree of the defining polynomial of the hypersurface V. I wrote there unbranched because algebraic geometers call cover also things that have a branching locus. So I want to be clear that this is just a standard topological covering, like you see in Hatcher's book, for example, or Moncrief's. Okay? This will be quite useful for us, right? So I have a finite cover of the complement of the projective hypersurface, and the covering space is this Milnor fiber, which is, well, relatively well studied. So if I want to understand V, I have a chance to first study F and then this covering map. And we'll see how this applies, for example, to calculate the Euler characteristic of the hypersurface, and this will be a very nice exercise. Okay? Feel free to interrupt me if you have questions. I have too many lights in my face to see hands, but I'll do my best. I see a hand. Do you have a question? All right, so let's continue. Yeah, go ahead.
Only a little bit. Why is covering?
Covering space. So you saw in, I think it's the simplest example of a fibration, if you like, where the fiber is a discrete set. So topological fibration is already something complicated. The covering space is something locally trivial, but the fiber is just a bunch of points. So this is just think, I don't know, think, what is the covering of a circle, for example? What are covering spaces of a circle? Well, the circle itself can wrap a bunch of times about the circle downstairs, or you can say I have this infinite spiral, which turns out to be the real line, which also covers the circle, right? And this is going to be an infinite cover, right? The number of points in the fiber is all the integers, while the circle covering itself a number of times is a finite cover. The number of times you wrap around the circle downstairs, right? Yeah? Yeah, I'm not sure the formal definition really brings any value here, but if you understand some examples, it should be good enough for following through what I want to say here. Okay? Yeah, so these are good questions. If you have something you're not comfortable with, if you see a term you haven't seen before, or you're not, aware of, just ask, okay? All right, so more terminology. So I said I have a hypersurface defined by f in both the projective space, but I can also take the zero set of f in the affine space of dimension 1 higher. And now I have a cone, right? So I have I'm going to draw a bad picture, but if this is the original f, if the original v hat is going to look like this. So this is the origin in the affine space, and then take all lines passing through the origin and this v, and you get the affine cone. So this is going to be v hat now. So this is my picture of v hat, and it has a bad singularity, a singularity at the origin. Now, if I intersect this v hat with a with a small sphere in the ambient space, what we get at the intersection is called the link. So this is very similar to the picture appearing in Milnor's book. Can I have the slides back, please? Is there any button I can press to get the slides back? Okay. All right, so what we have up there is the link at the origin in the affine space of this polynomial f. Okay. Milnor showed us that this link has a nice degree of connectivity, regardless how singular the polynomial f or the hypersurface v is. So the link is always, in this case, n-1 connected. Again, this means that the homotopy groups, or if you like, the homotopy type of the link is obtained from a point to which you start attaching cells of dimension n higher. Okay, now there is a Hopf bundle, so there is a standard fiber bundle that you see when you define the projective space. So there are various ways of looking at the projective space. You say this is the affine space Cn+2 minus the origin mod by C star, so lines through the origin in Cn+2. Or if you take unit vectors, this is the same as saying I'm taking the 2n+3 sphere, which is a sphere in Cn+2, and I project down, okay, onto the okay, so this map here from S2n+3 to Pn plus 1 is a tautological one. So just take a point in the 2n plus 3 sphere. So this is a point in Cn plus 2 and take its equivalence class in Cpn plus 1. So what you get in the fiber is going to be this time a circle. So this is called the Hopf bundle. And if I restrict it over the hypersurface in the base, the hypersurface V in the base, the effect up here is going to be that I have to intersect this sphere in Cn plus 2 by the affine cone on V. So we get the link, and the fiber is S1. So we get the Hopf bundle of the hypersurface V. So this is a fibration, and it's going to be very useful for calculations of homotopy groups. Okay, so why am I saying that? Because the circle is, you know, is what's called a spherical. It doesn't have homotopy groups except pi 1. So knowing that the link is highly connected will tell me that V is highly connected in some sense. We'll see this in a particular example in a minute. Okay, let me just say that, and you saw this already, and I will need this occasionally, that this version of the Miller fibration that I presented here in the global setup has a local analog. In fact, this is the Miller fibration that you see in singularity theory. And you have a Miller fiber and link associated to, in this case, a hypersurface singularity germ. So what I presented in our case was the story, the origin for this affine cone, but you can do this at any, for any complex hypersurface singularity germ. So this you saw already in Dirk's lecture yesterday. Okay. Let me start saying a few things about just some results. As I said, all the proofs and more examples are included in the lectures which are posted on the conference page. Let me just say that if you start with this Hopf bundle of V, the thing I mentioned earlier, with the link fibering over V, if I apply the homotopy sequence, the long exact sequence for homotopy groups for this bundle, we see that as long as n is at least 2, I said that kV is n minus 1 connected. So if n is at least 2, kV is going to be at least simply connected. And that's going to tell me that V is also at least simply connected. So if n is equal to 1, the best you can get is connectivity of V, but in higher dimensions, you get at least simply connectivity, if not more. Okay? So this says something about the fundamental group of projective hypersurface regardless of the singularities. Now, using some version of Poincaré duality, which is called Alexander duality, and this covering I mentioned, we can actually say something about, so I said I want to understand, for example, Betti numbers of the hypersurface, of the projective hypersurface. So one instance where the Betti numbers are as simple as they get, namely those of the projective space, is when this monodromy of the Milnor fiber of F doesn't have the eigenvalue 1. So the monodromy acts on F, is an automorphism of F. It induces a linear map on the homology or cohomology of this Milnor fiber of F, of the polynomial F. So the Milnor fiber, remember, was a level set of the homogeneous polynomial. This monodromy, I should say, is given by multiplication by a d root of unity. So it has order d itself. It is an algebraic map because F is an algebraic variety. You can diagonalize it in this case. In any case, if it doesn't have eigenvalue 1, if you cannot find the eigenvalue 1, then the cohomology of V with C coefficients is as simple as possible. I'm saying with C, with complex coefficients, because in general, it can be quite bad. And this is part of the next, well, this is the first exercise I want to actually consider during the exercise session. First, to show that, to show that this hypersurface has the same C cohomology as CPN. And I want to warn you, but this is a much more difficult thing to see, that the cohomology of such a hypersurface has torsion in general if you actually work with the integers as coefficients. So you shouldn't be fooled. Well, we don't care about torsion when we actually just look at Betti numbers, but if you want to understand integral cohomology, that's a much more complicated story. All right. Now, I said I still want to understand something about the topology of the hypersurface itself. And luckily, there is a nice result of Lefschetz, which says no matter how singular the hypersurface is, its cohomology, even integral cohomology, is the same as that of the ambient space up to the middle, or just below the middle. And then you have a monomorphism in the middle degree. The proof of this is quite surprisingly easy. Well, assuming you know something about the topology of affine varieties. And let me take this opportunity to say that many things I say in this talk apply much more generally to complete intersections. I do it for hypersurfaces because, well, you work with the polynomial instead of a bunch. But many of these results and their proofs apply to complete intersections. Now, this result tells us that I don't care how the hypersurface looks like from the point of view of singularity theory. The first half, or just below half of its cohomology, is simple. The question now is what happens with the other half, right? You have this thing in the middle where you have at least as much as the cohomology of the ambient space there, but then there is this other half. If the hypersurface happens to be smooth, then Poincaré duality will say, look, the other half is as easy as the first half, if you have no singularities. But of course, in the end, if you do singularity theory, most likely you expect some singularities to pop up. So you should be ready to understand the topology of a singular hypersurface. And we'll see that even the integral cohomology of a projective hypersurface in the second half of the range depends, in fact, on the dimension of the singular locus. Okay? Questions? All right. So this is good news. And since I said that the dependence from now on is going to be on the singular locus, I should start looking at some special situations from the least complicated to more and more complications. So the least complicated situation is that of a smooth hypersurface or non-singular hypersurface. I said that Lefschetz in this case and Poincaré duality is enough to tell us something about the Betti numbers except the one in the middle degree. But in fact, you can say much more. The whole topological type, or even diffeomorphism type of non-singular hypersurface depends only on the dimension of the hypersurface. So you saw yesterday in, I guess in Cesar's exercise session, that non-singularity implies manifold in the classical sense. So these are, at this point, manifolds. And what this result tells me is that, well, they are all diffeomorphic as long as I fix the degree. Okay, and moreover, even their complements are diffeomorphic. Now, there are a bunch of ways of seeing this, and one of them is based on Erasmus's fibration theorem that again popped up in Cesar's lecture, or you can simply say you can by hand construct an isotopy of the ambient space which takes one hypersurface onto the other. And that will be enough to prove this sort of result. Okay, so you can say now the smooth case is easy, but what do I do with the Betti number in the middle, for example? How do I handle that one? For that one, we use the Milnor fibration and the Euler characteristic. So if I know all the Betti numbers except the middle one, all I have to do to find the middle Betti number is to calculate, for example, the Euler characteristic. Now, the Milnor fiber is very easy to understand in this case, because if the polynomial is if f defines a non-singular hypersurface projectively, this means the affine cone has only an isolated singularity at the origin. I said all hypersurfaces which are defined by non-singular polynomials, homogeneous polynomials, are diffeomorphic, so I can work with the most convenient one, work with powers of d. Just take the, powers of d powers of the coordinates. So take the simplest degree d polynomial that is non-singular in projectively. So that's a sum of d powers of coordinates. Calculate the topology of the Milnor fiber for that. That's very easy, the Milnor number and all of that. Now the Milnor fiber covers the complement of the hypersurface V in the projective space. The Euler characteristic is multiplicative under finite covers, and it's additive for this kind of subsets. And this will tell you that you can actually calculate by hand, and I actually want to do this example, this result, I want to do it explicitly in the exercise session. It's a very nice calculation based on just the Milnor fibration. So this part here is going to be the Euler characteristic of the Milnor fiber F. This part, d minus 1 to n plus 2, is going to be the Milnor number at the origin for the affine cone. It sits in degree n plus 1, and this 1 is the contribution coming from the zeroth homology of F. Now, F is a default cover of the projective complement, so I'm dividing by d to move the picture downstairs. And then n plus 2 is the Euler characteristic of Pm plus 1. So by dividing the topology of F to the order of the covering, I get to the complement of V downstairs, but to get V out of that, I have to use additivity to subtract from the Euler characteristic of Cpm plus 1 that of the complement. So this is a very simple calculation. I guess I have 2 minutes, so I will just put down some examples and I'll stop here. So, exercise, which again we should work out today. If you work with a projective curve, a smooth projective curve, topologically this is just a Riemann surface, it has a genus. Show that the genus is computed by the degree, by that formula. This is the famous degree genus formula that appears in the theory of curves or Riemann surfaces. And the second example that I want to put here is, again, exercise. Is the following. Let's say I fix the Euler characteristic of the hypersurface, and I assume the hypersurface is non-singular. Let's say the Euler characteristic is that of the projective space Cpn. Question, is V the same as Cpn? Well, the answer is yes and no. I mean, yes in half cases, and yes with another possibility in the other half cases. So for people who saw the mathematics of the 70s, results of this sort were very fashionable back then. This particular instance This particular exercise appeared in some paper in Journal of Differential Geometry in the 70s, maybe 75 or something like this. Okay, so I will conclude with this calculation of Betti numbers now. So if I know the Euler characteristic of a non-singular projective hypersurface, and I have in my hands Lefschetz theorem, which gives me the Betti numbers below the middle, and Poincaré duality, which replicates these Betti numbers above the middle for V. Well, universal coefficient theorem tells me that the cohomology of such a non-singular hypersurface doesn't have any torsion in it, integrally. And the Betti numbers are given by this formula. So, of course, in odd degree, you get just the Betti numbers of the ambient projective space. For even degrees, except in the middle, you get again, the Betti numbers of the ambient projective space. And in the middle, you do this calculation based on the Euler characteristic, and you get this formula which tells you, as expected, that the Betti number, the nth Betti number, depends only on the degree and the dimension. Okay. Exercise just to play around with this formula. The more you see these formulas, the better use of them you can make in the future. Just try to calculate this for a smooth quartic. So degree 4 surface in CP3. I will start here after the break. So after the break, I want to start this discussion about what happens now if our projective hypersurface is allowed to have singularities. And we'll see that in this case, a lot of stuff can happen, even perhaps more complicated than expected. And this is, again, mathematics of the 30s from Lefschetz and Zariski and so on. Okay, I'll stop here. Bad memory. All right, so let's see what happens if we have singularities. So in this case, there is a result of Kato, which again holds more generally for complete intersections. Let me just state it here for hypersurfaces. Let's say we have a hypersurface of degree D, which has a singular locus of dimension S. Then the cohomology of the hypersurface is the same as that of the ambient projective space, but now at the end of the spectrum, at the end of range towards the top, and that range depends on the dimension of the singular locus. So this is S coming up here. Okay, so this, well, if S is -1, if you're in the non-singular case, this is of course not unexpected, because we know by Poincaré duality we should have something like this already, from n+1 to 2n. But this says that you can put anything here, any dimension, and you still get some part of the cohomology of the projective hypersurface being the same as that of the ambient space. Moreover, the inclusion, so these guys are Z and Z, but the map from Z to Z induced by inclusion is in fact multiplication by D, provided these groups are not trivial, right? So in the even case, the inclusion induces in this range multiplication by D. So this is quite useful, but it still leaves a range of groups from between n and n plus s plus 1 as being the dimension of the singular locus, which we don't know yet anything about. Now, this result was proved in the 70s by Kato. This is the same Kato as Kato Matsumoto, and this paper followed immediately after the one where they proved the connectivity of the mineral fiber. Okay, a nice proof by Alex Dimka of this result uses the connectivity of the mineral fiber of the polynomial f, as I defined in the beginning of the presentation, and various other things based on Gizen sequences for various bundles. In this case, the Hopf bundles of V and the projective space. As I said, the result holds more generally for complete intersection, but the proof is much more complicated. So, but still doable. Okay, so this, I should point out that, well, let me first discuss an exercise here. So we take a projective hypersurface which has the same integral cohomology algebra as CPN. So this is it's much more than just the cohomology groups integrally being the same as those of CPN. I want the whole algebra with the cup product and all of that to be the same as that of CPN. Show that if n is at least 2, then the hypersurface is CPN, is isomorphic to CPN as a variety. So this is quite strong already. So we saw earlier some conditions for our hypersurface to have the same cohomology over the complex numbers as those of CPN. Now I'm saying if a projective hypersurface has the same Z cohomology CPN as an algebra, so with the cup product, you take the cup product into account, then the variety is, so this information, the Z cohomology algebra is strong enough to tell me that you actually have CPN in place. So topology, just the topological information, homotopy theoretic information on the hypersurface V will tell you the algebraic structure of the hypersurface. So this is a quite powerful result. N is at least 2 there, and this is necessary because, well, there are examples for curves. For example, take the cuspidal curve and project it on the line, and you'll see, of course, that. So if you have something like this, and I project from the cusp, so a point here goes to a point here, so this is P1, this is a cuspidal curve, and so on, right? This point projects down along the tangent. This projection gives me a homeomorphism between the cuspidal curve and CP1. Being homeomorphic, of course, they have the same Z cohomology, even as algebras. But of course, the cuspidal curve is not isomorphic to CP1. So the assumption that n is equal to 1 is essential in the exercise up there. This is a very cool exercise. I actually encourage everyone to try to work it out. It's based on this Kato result that, well, in fact, in this case, it's just this second statement here that the cohomology in the top degree, for example, is multiplication by D, D being the degree of the hypersurface. Okay, and finally, and this is where it's a good stopping point, I want to point out that I don't want to mislead you, to give you this impression that the cohomology of a projective hypersurface is almost all the time that of the ambient projective space. It's quite far from that, even though the results of Lefschetz and Kato point in that direction. You have this beginning and ending of the range of the cohomology, which is the same as that of the ambient projective space. In general, in this tricky range just above the middle, up to the Kato range, things can be quite different. And this is the example that I want to give, which is already from Zariskis from the 30s, that the Bethe numbers in this range depend on what's called the position of singularities. So you may have hypersurfaces that look alike, they have the same number of singularities, the same type of singularities, but somehow they sit differently in the ambient space, and that will mess up the Bethe numbers. So this is the example. Take a surface in CP3. So this is built up from a curve of degree 6, called here C6, defined by the polynomial f, with only 6 cusps as singular points, and then add a new variable to power 6. So this surface is, well, it's a branch cover over the complement of C6 in CP2. Anyways, doesn't matter. It's a branch cover of CP2 over C6. But it's a surface in CP3. And now if the 6 cusps of the curve within CP2 are situated on a conic, I give you an example when that happens. Again, these are classical things. Then the second Bethe number, so this is a surface, right? So the ambiguity in Bethe number starts at the middle, B2. So B2 in this special situation where the singularities are in a special position on a conic, this B2 of the surface is 2. But in the general situation, when you don't expect 6 points to sit on a conic, so this is the generic situation, you get the second Bethe number to be equal to 1. So the reason here, and this is something that Zariski explained, is that while the two types of sextic curves, so this C6 that I put on the board here, they are homeomorphic, one cannot be moved onto the other by some deformation. There is a moduli space of such curves which has 2 components. All right, so now I think it's time to stop, right? Good. I will stop here and I will continue with the general situation after a break.
Okay, I think we can start again.
Okay. So now I can talk till we all get very hungry. All right, so I will move now to say something about Betty numbers or cohomology, integral cohomology of hypersurfaces in the range. Maybe I should draw a picture here so that we're all on the same page. The slides may not always be there. So if I have V of dimension n in CPn plus 1, and S is the dimension of the singular locus, then I'm going to start the cohomology indexing from 0 to the middle, then n plus 1, then we have n plus s plus 1, and n plus s plus 2 up to 2n. So now we have this range here, which is covered by Lefschetz. Then we had this range here that's covered by Kato. So these two statements told us that the cohomology in these ranges is essentially the same as that of CPn, CPn plus 1 or CPn. And then the question is what happens in the middle, right? So this is something that I would like to address now. So there is this range not covered by any of these classical results. All right, so in this case, I'm going to start doing the general situation here. It's a standard construction, but if you haven't seen it before, it's perhaps a good idea to try to pay attention a little bit. So what I'm going to do is I'm going to take my singular hypersurface and put it in a family of hypersurfaces. But a family of hypersurfaces will have, not only in a family, I would like to put it in a fibration somehow, with the general fiber being a smooth hypersurface and the singular fiber or the zero fiber of the family being the given hypersurface. So this is what I'm doing, what I'm trying to do here. So first, I consider what's called the one-parameter smoothing of degree d. So what I'm doing is I'm taking a general polynomial of degree d, general in the sense of transversality. I'll explain in a second. And I'm going to take f minus t, t being a new variable, times this general polynomial. And I get the polynomial ft, now depending also on t. This defines a projective hypersurface, call it vt. Now for t not 0, small enough, vt will be smooth and it will be transversal to the strata in a stratification of v. So this is the meaning of this genericity of the polynomial g. But you see, now I don't quite have a fibration yet. So what I have is a bunch of hypersurfaces depending on a parameter t. I have the initial hypersurface for t is equal to 0 and the nearby ones being smooth. So I have what's called a pencil of hypersurfaces. To actually create a fibration out of this pencil, to somehow, so a pencil looks like, well, I'm going to draw something bad here, but please bear with me. So let's say I have, well, maybe like this, something like this, and then I start having things, other hypersurfaces going like this. So this is the original one, V0, and here I have a VT. Even though I drew them as lines and curves, they are all supposed to be hypersurfaces of the same degree. So now they have something in common here, which I want to blow up so that these things now become, they spread out. So I'm going to replace this bad point, this base locus, by a line, a projective line or a disk. And then I have the original hypersurface V0, and then nearby I'm going to have this VT, and so on here. So this is what I would like to do, and how do I do this formally? So this blowing up of this base locus, What is the base locus? Well, it's the locus where F and G both vanish. Blowing it up is the same as working with this, also called incidence variety. So this is, it's just the correspondence, right? So I'm collecting X and T's, X being in the ambient space and T in a small disk near the origin, so that the point X is in the hypersurface corresponding to the parameter T. So this VD is going to be this family I put up here. This is going to be our VD, and of course it projects down to D, to the disk. Okay. So now I have this projection. It's a proper map, proper, because the fibers of this map are, as I wrote there, the zeroth fiber is the original hypersurface V or V0, and the nearby fibers are this hypersurface is VT. Of course, these are all compact. But now VT sits near V, and it is smooth. So this VT is going to be called the smoothing of the hypersurface V or V0. So now I created a fibration where in a tiny somehow neighborhood of this singular hypersurface, and the fibration is over D star or C star, whatever I work here with, D star, the puncture disk. So I have a fibration over a puncture disk, and you can think of this as a family of hypersurfaces degenerating to this zero fiber. So a bunch of hypersurfaces moving closer and closer to the origin till eventually some degeneration appears over the origin, they acquire singularities. Okay, now in algebraic geometry there is a classical theory that tells you how you can study the singular, the fiber here, this is the singular fiber, by looking at the nearby smooth fiber, and since we have a fibration over a disk, we're going to have a monodromy again, or puncture disk here. We're going to have a monodromy which is going to tell us what's going to happen if I circle a generator of this star downstairs. So here is going to create a homeomorphism of the general fiber. So the monodromy of this family and the topology of the smoothing should tell us something about the topology of the singular hypersurface. Yeah, so this is a classical story. So now, of course, I don't want to get too much into details about this. I'm going to use some fancy language a little bit. I said more in the notes, so I actually invite you to look at the video recording for the lecture about specialization. So there is a nice way, just like in the case of mineral fibers, of moving topologically from the nearby fiber to the singular fiber. So there is a nice geometric way of moving from one fiber to the other, and this is called specialization. So this is what I want to discuss here. So first, this ambient incidence variety now is not the projective space anymore. It's some variety in CPn plus 1 times a disk, and it still has complex dimension n plus 1. So you can think of it as a waving inside of the ambient space. And in general, yeah, maybe I should not say in general first. I should say that this ambient space, this VD, this total space of the family, is non-singular if we only have isolated singularities on the original hypersurface V, but in general it is singular where the base locus intersects the singular locus of V. This is not so important for what I want to say next, but for people who like details, maybe this will turn out to be an essential story. Okay, so now this is the fanciest part of this presentation, which I'm just gonna want to swipe under the rug. There is someone named Delin, who perhaps you heard of, also a Fields medalist, who said, look, whenever you have a mapping, algebraic, analytic, doesn't matter, there is some complex associated to it, a complex of sheaves now, which, well, it's called the vanishing cycle complex. It has some letters, phi, sub the map, in our case is pi, and then what I put there has to do with the coefficients we work with. So A is either Z or a field in our case, and this other scary symbol here is the constant sheaf on the ambient set VD with coefficients in A. Anyways, don't worry too much about this. This is something that collects the Milnor fiber information locally, the singularities locally. So it is supported on the singular locus of the hypersurface, and it encodes at every point in this hypersurface the Milnor fiber cohomology at those points. So if you like, what are sheaves? Sheaves are things supposed to relate local and global picture, right? So they take this piece of local information from all over the place, and they put it together in a global object, so to speak. So this is a complex of sheaves. It's defined on the whole space. As I said, it's supported on the singular locus of the hypersurface. But if I specialize this complex of sheaves at some point, what I see there is the cohomology of the Milnor fiber at that point. All cohomology groups of the Milnor fiber, or reduced cohomology groups of the Milnor fiber at that point. So point by point, I just see the Milnor fiber cohomology, but this is a neat way of putting all of this information together. All right, we'll see in a minute that there's not much behind this in our situation. This is classical topology. I wanted to put it here because, you know, if you want to actually prove results I'm going to mention here, you have to use this properties of this complex. Now, this complex fits into what's called a specialization sequence. Again, this is something that relates the cohomology of the given hypersurface to that of the smoothing. So this is the map from VT to V0. In cohomology is going to give me this map here. And then this vanishing cycle complex has cohomology groups associated to it. And those cohomology groups really record the difference, so to speak, between the cohomology of the given hypersurface and that of the smoothing of the same degree. So this is a way of packaging somehow. Why am I doing this? I know the topology of a smooth hypersurface, right? I said that on the previous slides. So I know all cohomology of a smooth projective hypersurface of degree D. I want to understand the cohomology of a projective hypersurface of degree D, but with arbitrary singularities. The difference between these two guys is going to be measured by the cohomology, or better said, hypercohomology groups of this new complex of vanishing cycles. If you actually, maybe I should write down what I mean by this. There is a nice observation here that I should say that initially, I mean, many people have worked on this, but by various techniques. So Parushinsky-Pragas are the ones who initially studied the cohomology, even I guess the Euler characteristics of hypersurfaces with arbitrary singularities. And they noticed that there are no vanishing cycles along the base locus. So here I said this complex of vanishing cycles is supported on the singular locus. The singular locus intersects the base locus, and I said those are the places where this ambient space VD has singularities. But in fact, wherever the singularities of V intersect the base locus, this complex is trivial. If you like the terminology of the Milnor fibration, the Milnor fibers of the map, of this deformation map pi, this family, at points along the base locus is contractible, so its reduced cohomology is trivial. This is just a technicality which explains what you'll see on the next slide. So the base locus somehow is complicated, but it doesn't give us topology. The upshot here is that this vanishing cycles really records the difference between the cohomology of the given hypersurface and that of the smoothing, which we know. So we know this, we want to find this. And if I understand the third term, this difference term, we're in good shape. All right, so let me say something about the Euler characteristic. So if I have, what did I have? I had this long exact sequence, right? So if I apply the Euler characteristic to this, this will say the Euler characteristic of Vt is the Euler characteristic of V plus the Euler characteristic of this complex, whatever that is. So there are techniques in homological algebra which are very well adapted for calculating Euler characteristics of complexes in terms of stratifications. And as I said, over a stratum in V, this complex really records just the minor fiber information at points in that stratum. So what we get by taking the Euler characteristic in the previous sequence is this result of Parushinsky-Pragash, which was reformulated later on by myself and Saito and Schurman in the Hoche theoretic setting even, is that once you fix a stratification of your hypersurface, again, the technical term is Whitney, but what this really says is that the hypersurface is supposed to be equisingular along each stratum. So each stratum should really contain all points which really look alike from the singularity theoretic point of view. Then, if I take a smoothing, so this would be, for example, defined by a generic degree D polynomial, so the same degree, and genericity translates into the fact that this W, which is a manifold, is transversal to all the strata of V. Again, generic can be understood in many ways, but in this case has a geometric interpretation. Then, and here is the answer. How do you calculate the Euler characteristic of any hypersurface V? Any singularities? So what do I have? I have the Euler characteristic of a smooth hypersurface of the same degree. So that was Vt on the previous slide in the specialization, from which I subtract some things. The whole part that I'm subtracting here is the Euler characteristic of this vanishing cycle complex. Here I have strata, but you see I'm throwing out, from strata I'm throwing out their intersection with this smoothing, with this W. What is that? I'm throwing out the base locus. Why am I throwing out the base locus? Because I said the base locus doesn't contribute any topology from the point of view of vanishing cycles. What are these mu s here? So these are invariants associated to each stratum of the hypersurface V, and they are exactly the Euler characteristic of reduced cohomologies of minor fibers over those strata. I said the minor fibers at points in the base locus are contractible, so that's why I have to throw out, well, I don't have to throw out, but if I keep the Euler characteristic of S here, it's not going to make any difference, because over its intersection of S with the base locus, this mu S is trivial. So for computational purposes, this is the most efficient formula one can think of in terms of calculating the Euler characteristic of a projective hypersurface with any kinds of singularities. So I have again, the Euler characteristic of a smooth hypersurface of the same degree, which we know. We had the formula in the previous presentation earlier, from which we throw out some things which are essentially minor informations concentrated along strata of the hypersurface V. We'll see this in examples. Of course, in general, dealing with Whitney stratifications and calculating Euler characteristics of minor fibers and Euler characteristics of strata is not an easy task. But case by case, and we'll see that in examples, case by case, one can get a lot of mileage out of this. Maybe Matthias and Anne can actually implement this into, winning stratifications is a good thing to have, and the rest is essentially just numerical calculation. That would be very useful for many people. Yeah. All right. So here is some example. Let's say you have only isolated singularities. What do I have here? Well, this formula looks a bit scary, but it's in fact very, very easy. Why? By the way, I should say you'll see some of these formulas appearing in Dirk's talk at some point for hypersurfaces with singularities of dimension up to 1, but from a more geometric point of view. So what do we see here? Well, the first part of the formula is the Euler characteristic of a smooth hypersurface of the same degree. This is what we had earlier. What you get here is the correction term, the second term here. So what do we get? I said vanishing cycles are supported, localized at the singularities of V, where they see the Milnor fiber information. Well, at an isolated singularity, the Milnor fiber is a bouquet of spheres. How many? The Milnor numbers of each of those local singularities. Those are the things that come up here. And of course, the strata in this case are just points. So zero-dimensional, and they don't intersect the base locus. So the Euler characteristic is 1, and this is our formula. So the Euler characteristic of a projective hypersurface with only isolated singularities is that of a smooth hypersurface of the same degree, corrected by, up to a sign, the sum of Milnor numbers of the singular points. Yes, go ahead.
Well, I have a question. Well, we know that degree depends of the projective of the embedding in the projected space. So I was curious. Well, if that formula also takes account of that fact.
So the degree here, since you work with a hypersurface, is just the degree of the defining polynomial.
Okay. But we know that degree depends of the projective embedding. I'm wrong.
Yeah, here I'm fixing the embedding. I work with a fixed ambient space.
Well, for me, it's very impressive that like even when we change the embedding, because the Euler characteristic is constant, isn't it? It doesn't depend of the embedding.
Well, when so you see this inclusion here, this fixes the embedding. I'm not claiming that you change things around. Of course, if you change things around, you may change singularities also.
Mm-hmm.
You may change the whole structure here.
Okay, I see.
You may not, just like with a circle, you may not a circle more. It still sits in an ambient space, but it's embedded differently. You get a completely different knot. Of course, you can do the same here, but then you have to change this formula. You have to change this contribution. Only the smooth part will stay the same.
Yes, but I remember that we have a formula for the smooth case, I guess. But anyway, I understand at that point.
We can discuss more if you have any puzzlement about this. I will do some examples in the lecture, in the exercise session, and hopefully this will clarify some matters.
Okay, thank you.
So this is still a very kind of general formula. So what I want to actually get down to, and this is an exercise that I would like to work out with you in the exercise session, is let's say we work with a curve, but now with singularities, a reduced curve with some singularities. B0, well, the zeroth Betti number is 1 because this is a connected thing. B2 is going to be the number of irreducible components. And B1 is going to be computed from the Euler characteristic formula. And, well, it depends on the number of components, the degree, and these Milnor numbers at singularities. So, of course, this is an exercise that just, it's very simple-minded, but it shows how to At least for curves, you know everything. Let me put it this way. Singular or not. We already saw the smooth curves. Those are essentially determined by the genus. Of course, they are Riemann surfaces. But in the singular case, we can still do all the calculation. Here's a more concrete example. I think this appeared maybe in Cesar's, I don't remember, or maybe Dirk's exercises yesterday. So have a curve in P2 defined by XYZ equals 0 and calculate its Betti number. So I wrote the answers, but of course, we have to calculate the singular points, Miller numbers, and plug into these formulas. Okay. There is a very nice class. You see, I'm telling you here that if I work over Z, I have this table. But what if you work over the rationals or over C? Well, there is still chance of actually understanding the second half. So this guy is already special because he's right in the middle. But the second half could still be replicating the first half of Betti numbers, because Betti numbers don't see torsion, right? Provided you have some sort of duality over a field. And rational homology manifolds are very nice examples of spaces that still have Poincare duality over rationals. So what is a rational homology manifold? Well, what is a topological manifold? A topological manifold says at every point, after taking a small ball around that point in your manifold, and the boundary of that, the boundary is topologically a sphere. It's homeomorphic to a sphere. A rational homology manifold will say that boundary, which is also called the link of every point in your space, has the rational homology of a sphere of the right dimension. So these are called rational homology manifolds. For hypersurfaces, we'll see there is a nice way with singularities to decide when a hypersurface is a rational homology manifold. I'll mention that in a minute. But then, if you have a rational homology manifold, you have Lefschetz, which tells you what the Betti numbers below the middle are. Poincare duality over the rationals is going to tell you what the Betti numbers above the middle are, and then you get the Betti number in the middle from the Euler characteristic formula. So in this case, everything is already computable. Okay, we'll get back to more specific things about rational homology manifolds in a minute. Let me get back to this vanishing cohomology, right? So I said, if I want to understand the integral, not just the Euler characteristic, but now the integral cohomology of hypersurface with arbitrary singularities, I have to look at the specialization sequence, which related the topology of the hypersurface with that of the smoothing, and the correction or the difference is measured by these vanishing cycles. So there are these maps carry names coming from the lean. This SP comes from the specialization. This map I told you that one can define here. While this CAN is it comes from canonical, not from the tin can. It's a canonical morphism. The cohomology of the smoothing of VT is also called the nearby cohomology. So the cohomology of a nearby fiber of the family. All right, here we go. So reformulating things in more down-to-earth term. So the incidence variety, which is the family of, the total space of this family, by properness, the formation retracts to the zero fiber of the family. So the first term here in the specialization sequence is nothing but the cohomology of this space VD. And then I have the cohomology of this VT, which is a subset of VD. Well, every third term has to be the relative cohomology. So this vanishing cohomology is nothing but the relative cohomology of this total space of the family, of the smoothing, relative to a general member of the family, which was a smooth hypersurface. So this is how you'll see this in maybe the lectures by Dirk, because in a paper with Mihai Tibor, they have the homology analogs of this vanishing cohomology group. So we call these guys here vanishing cohomology groups. So these are the correction terms in the specialization sequence, right? So these guys will be called vanishing cohomology groups, and I even put some more symbols to denote it, just replicating essentially what Dirk and Mihai did in their paper for hypersurfaces with one-dimensional singularities. So I should say that this is, I mean, it already appears in Mihai's book, this notion, at least in the local situation, also Neumann and Nurbury, I guess. So it's a known thing, this vanishing homology or vanishing cohomology, especially for polynomial maps. Okay, this is an adaptation of the more classical situation to the projective situation, to the projective case. Okay, so now we have some gadget, this vanishing cohomology, which in principle, if we understand, since we know the cohomology of the smoothing, we should be able to say something about the cohomology of the given singular hypersurface. So this is a result in a paper with Mihai Tibor and Laurențiu Păunescu, which generalizes something that Dirk and Mihai did in the one-dimensional singularity case. Says, well, this vanishing cohomology is concentrated also. It's not, it vanishes below n and above n plus s as being the dimension of the singular locus. At least the proof we gave here uses this properties of vanishing cycles and so on, homological algebra. So that's why we could not work just with the relative cohomology groups like it is possible in the one-dimensional singularity case, as you'll see in Dirk's talk. All right, so vanishing cohomology vanishes. Well, by duality, vanishing homology vanishes. Anyways, this is just a direct consequence by the universal coefficient theorem in a similar range. What are the benefits of this vanishing? Remember, I have this specialization sequence, right? And these groups, these vanishing homology groups, cohomology groups, or every third term in those sequences. So vanishing of every third term in some range will tell me the remaining two terms will be isomorphic, right? Okay, that's not a surprise because those isomorphisms will appear exactly in the Lefschetz and Kato range. So we recover in this way Lefschetz and Kato. So the first bullet there says that the cohomology of the hypersurface with any singularities, dimension S, is the same as that of the projective space in this, away from this range, away from the question mark range, which we already knew, but this is yet another proof of that fact. All right, but then it also tells us something else, says something about the middle group being free. So I should take you back to the specialization sequence. So these canonical maps, what are they? Let me put them. So the canonical maps were defined on the Kate cohomology of the smoothing with integer coefficients to this vanishing homology. So now the vanishing of things of this sort in some range will tell us something about the remaining terms of the sequence. So let's get back to the corollary. So we get a bunch of results which essentially write down the integral cohomology of the hypersurface in terms of various kernels and co-kernels of these canonical maps. So this is in the range that we didn't know anything about before, right? I should warn you that this is by no means a final answer. I mean, what are the canonical maps? That's yet another piece of the story, and that's actually very complicated. But again, case by case, one may be able to get some mileage out of this. In terms of Betty numbers, okay, we get estimates in the range not known before. In terms of these vanishing cohomology groups. As I said earlier, these vanishing cohomology groups are somehow manageable in principle by looking at, by using homological algebra techniques. So I want to actually give you some result in that direction, but maybe let me mention again that for isolated singularities, these results, this situation was already studied by Dimka, and then as I mentioned already, in the case of one-dimensional singularities, Mihai and Dirk obtained similar results. This is the general situation that one can get for arbitrary singularities. Okay. Torsion, well, I'm not sure I want to. So as I said here on the previous slide, these cohomologies of the hypersurface are kernels and co-kernels of canonical maps. Kernels are always subspaces or subgroups of cohomology of the smooth hypersurface, which we know are torsion-free. So the kernels don't contribute to torsion, only the co-kernels do. So at least we know where the torsion in the integral cohomology of a hypersurface can come from. All right, so yeah, so this is what I'm saying here. Let me skip this because it's very simple. Exercise. So I'm gonna bring the slides up when we have the problem sessions. So the remaining sessions for me will be exercises once I'm done with the slides. Consider a very specific surface. Well, this is a projective cone on the curve I put up earlier. And now I'm asking, calculate all the integral cohomology of this curve, of this surface, and if possible, try to calculate the vanishing cohomology. So vanishing cohomology pops up only in 2 degrees here. One is free, the other one is whatever. And in fact, both of them are free, and they are computed by I think this result already appeared maybe in Dirk's and Mihai's paper. Yes. You'll have it too, maybe. You'll have it as an exercise. Maybe you solve it. All right. So anyways, this is a cute exercise that I encourage everyone to try. And now, well, let's do something more, right? So I gave you some estimates. I gave you some, I told you the integral cohomology is written in terms of kernels and co-kernels of these canonical maps, and the Betty numbers essentially are bounded above by the ranks of the vanishing cohomology. Well, we can do something very precise about this one, about the top Betty number in the range not covered by Kato. So here is the statement. For each, so stratify our hypersurface as singularities of dimension S, stratified. The top singular strata are going to have dimension S. Look in the transversal direction to the stratum. Consider the minor fibrations there. Now, in the transversal direction to a top dimensional stratum, you're going to have an isolated singularity. The minor fiber in the for that transversal minor, the minor fiber for the transversal minor fibration is going to be a bouquet of spheres of the right dimension, and let that number of spheres be this mu I transverse. So this is essentially recording the number of vanishing cycles in the transversal direction to a top dimensional stratum. There may be a bunch of them, right? Singular locus is not necessarily connected. Then, this Betty number that I'm pointing out here is bounded above by, we already saw on the slide, it was 1 plus the rank of some vanishing cycle, vanishing cohomology. That vanishing cohomology has rank exactly equal to the sum of the transversal minor numbers. And you can say when the inequality is strict and so on. So this gives you some manageable upper bounds. We'll see in a minute, this is the best you can do, actually. But homological algebra, I'll give some references at the end, will give you some bound for at least the top Betti number that's not covered by Kato and Lefschetz. Okay, in the isolated singularity case, of course, these isolated singularity points are going to be the top singular strata, and the transversal minimal fibrations are going to be the actual minimal fibrations. So there you get the actual minimal numbers. So if S is equal to 0, this will tell me that in that case you have two Betti numbers to worry about for V, Bn and Bn plus 1. Bn plus 1 is is less or equal than 1 plus the sum of minimal numbers at the singular points. All right. Good. So, exercise. I want to point out that this bound is sharp. So there is an example where you actually calculate the Betti number and you get exactly what the bound tells you should get. And this says to, well, these are quadrics, right? So I put it here as an exercise. I'm not sure it is worked out in the notes, but we can try at least to move into this direction. The calculation is ad hoc, right? Because we don't, I didn't give you an efficient way of calculating the cohomology of a hypersurface, right? So I'm giving you here some specific equation. Okay, I'm almost done. And by some method, you calculate the cohomology. The bound you'd get from the previous result would be 2 on this Bn plus S plus 1, but by calculations, by ad hoc methods, you get actual 2. So the upper bound is sharp. Okay, so I was shown this sign, which means I should cut soon. So let me just conclude with this result here, which says, if you have singularities as bad as it gets, so in codimension 1, then Bn plus S plus 1, this guy is exactly the top one. So Kato doesn't do anything for us in this case. And that is known by classical topology. It is the number of irreducible components of the hypersurface. Again, what is it? I should have said this. So if I have a polynomial defining V, that polynomial is not necessarily irreducible. So it decomposes into irreducible factors. The number of factors is this R. Okay? And in this case, the bound I gave earlier will tell us, well, since I already know what this number is the number of irreducible components, that irreducible component has, the number of irreducible component gets a bound in terms of the Betti numbers. This is something that I guess Dirk and Mihai did for surfaces, and we saw that you can generalize it to arbitrary things using these methods. All right. Now, there is more here about rational homology manifolds. I will work some of these things out in the exercises. So I said I wanted to say something about rational homology manifolds. I will just skim through it. Don't worry too much about this. I want to get to some exercise. So some hypersurface, which is a rational homology manifold, it has a one-dimensional singularity. Calculating its order characteristic is not that immediate, so you have to apply to use the formula that I put on the board earlier, find the stratification and so on. But being a rational homology manifold, the only Betti number that's unknown is the middle one. So if you know the Euler characteristic, that Betti number will be deduced from the Euler characteristic. So I gave you here the stratification. We'll work this out later on. There is more stuff, don't worry about this. I want to end with this. So references. A very nice introduction to singularities of all sorts is this book by Alex Dimka called Singularities and Topology of Hypersurfaces. I think after Milnor's book on minimal fibration, this is the second best reference. Alex Dimka has another book called Shifts on Manifolds, which has more souped-up versions of singularities using shift theoretic methods. I also wrote a book where I emphasize more the part coming from intersection homology and perverse sheaves. chapter 10 in that book has to do with vanishing cycles, so it's maybe a good reference for someone who wants to learn about vanishing cycles. I emphasize this story about vanishing cycles and more applications and other variants of it in some survey I wrote not long ago. And then the remaining two papers are these papers I was talking about. So the one I talked about here was this number 4. And similar methods apply locally in the non-isolated singularities. You saw something like this already yesterday in Dirk's talk. For one-dimensional singularities, using these methods, you can push the boundaries to arbitrary singularities and get, this kind of qualitative results, right? So they don't really do the calculation for you, but they give you the vanishing, they give you some information about freeness, where the torsion comes in, and things like this. Okay, thank you very much. I'll see you in the afternoon.
Okay, thank you. Nice talk. Are there any questions, comments? Yes.
Do you have version for affine? Complex
That's
affine?
yes, so there are ways of doing something in the affine situation using similar techniques, but of course you get the results are, you recover what's known, the connectivity of the Milnor fiber and things like this, bounds for the first Betty. So in the affine case, if you work with the polynomial map, the question is, as you saw in Cesar's talk, well, first detect the bifurcation set, okay? But then once you know that, let's say you have an atypical fiber and a typical fiber. You want to understand their cohomology also, right? Or their Betty numbers or something. So now you have some homotopical connectivity, which you can recover by this kind of methods in the homological or cohomological sense. The typical, the smooth fiber, the general fiber will have the degree of connectivity 1 higher than the typical, the atypical fiber. And then what we get new is upper bounds for the first non-trivial cohomology popping up in terms of this transversal Milnor numbers and so on. But it's a mild improvement from what, for example, you can find in Dimka's book on shifts on manifolds, though there maybe he emphasizes this tameness at infinity and so on. So they like to work with good properties at infinity, maybe only isolated singularities at infinity or something like this. So what we can do is for any polynomial, but you get only some new information for the first, just like here, right? So you get bounds for, here I got it for the first not covered by previous results. In the affine case, you get, so you have vanishing, 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 and then the first thing that pops up, we have bounds in terms of local information.
Anything else?
And by the way, I should say this also works locally, like in the, so the thing I said is, yeah, this doesn't work anymore. The thing I said is very similar to that last paper I put there on the board. So for the you locally have the connectivity of the Milnor fiber, and then the first non-vanishing cohomology of the Milnor fiber, what is it? And that Betty number, you can find upper bounds on it based on local singularity, so to speak, based on the stratification.
Okay, so let's thanks Laurencio.
Thank you.